This video is going to talk about molecular geometry, which is basically just telling us the shape of an atom. When we do a Lewis structure, which is going to be the first step here, it's just two-dimensional. But molecules in the real world are actually three-dimensional. So that takes us to something called VSEPR theory, which stands for valence shell electron pair repulsion. VSEPR theory has to do with the repulsion between electrons. So you know that electrons are all negatively charged, so they all repel each other. However, these atoms are also bonded to each other, so there's competing differences here. Bonding wanting to happen, repulsion wanting to make that not happen. So what will happen is they will bond. The desire for atoms to bond is strong enough that it will happen, but they will then be as far away from each other as possible while still being bonded. And that's where VSEPR comes in. So in order to figure out the shape, we're going to draw the Lewis structure, count the number of electron domains, I'll explain what that is, split them up, electron domains or electron groups, the same thing, into bond groups and lone pairs, and then use this chart. So on your notes, you'll see that you have a chart. I split it up into two slides here, but you have this. It's in the notes. So let's get started. I'm not going to go through how to do the Lewis structure for these. If you go back to the Lewis structure video, you can look at that yourself, but I'm just going to draw them right away so that I can get to the geometry part. So this is the Lewis structure for BF3. Remember that boron is one of our octet exceptions. It only needs 6 to be happy, so there's no double bond needed here. Okay. So after you have the Lewis structure, you're then going to count the electron domains around the central atom. So what that means is you count the bond groups or the lone pairs, but only around the central atom. So we don't care about these lone pairs around fluorine. So here around boron, we have 3 bonds, 3 electron domains. So I'm going to put E groups, which is the same as an electron domain, and then I'm going to separate those into bonds and lone pairs. The E groups here around boron are 3. All 3 of those are bonds, and so 0 of them are lone pairs. 3, 3, 0. When you're doing this, these 2 columns should always add up to this column. Once you've done that, you go up here, electron domains 3, bond groups 3, lone pairs 0. That is something called trigonal planar. And then every bond angle is going to be 120 degrees. So this is trigonal planar. And if someone asked you the bond angle, you would say they are all 120. And that's pretty easy to draw. You would just draw them like this. And we'll go over that in class. We're going to do an activity so you can see these shapes themselves in 3D. So now let's do ZEF4. I did do that one for you in a prior video, so you can go and take a look at the Lewis structure for it. If you aren't sure how I got this, it's an expanded octet. So now we're going to take a look at the E groups around the central atom. We have 4 bonds and 2 lone pairs. So that's a total of 6 E groups. 4 of them are bond groups and 2 are lone pairs. So we go up to our chart. 6, 4, 2 is square planar. And the bond angle between all of the terminal atoms is going to be 90 degrees. So I'll do a couple more examples for you. NH3, the Lewis structure looks like this. So when we do our E groups, our bonds, and our lone pairs, remember around the central atom, we have 4 E groups. 3 of those groups are bonds, and 1 is a lone pair. So if you use the chart, 4, 3, 1, 4, 3, 1, trigonal pyramidal. And again, we'll have an activity in class where you can see those shapes. If you missed class for that day, feel free to Google the shapes and I'm sure you can find plenty of drawings of them. For water, we have 4 groups. 2 of them are bonds and 2 of them are lone pairs. So if we go to our chart, 4, 2, 2 is a bent shape. And you've probably seen this before. You would see water written like this. And that is because there are 2 lone pairs at the top pushing down those bonds. Because remember, bonds are made up of electrons. Lone pairs are made up of electrons. So they're all repelling each other as much as possible. And so what happens is you get this bent shape. That bent shape for water is very, very important for something we're going to do later in this unit, because it does determine a lot of how our world operates, that bent shape. All right, so 2 more. We have CH4. Four groups. And they are all bond groups. So 440, very common one, is tetrahedral. You notice the bond angle is a little weird in tetrahedral, 109.5. That is what happens when they all repel each other as much as possible. And then the last one I want to do is CO2. We've done the Lewis structure for CO2, and we know that it looks like this. Whoops. So around our central atom, we have these 2 double bonds. A double or triple bond counts as 1 electron domain and 1 bond group. So here we just have 2 electron groups, and both of them are bonds. If they're a double or triple bond, they count as 1 group. That's very important to know, because that's going to make this a linear shape. If you didn't know that and you tried to do 440, you'd get tetrahedral, which doesn't make sense because we don't have 4 terminal atoms, so we can't have tetrahedral here. So you have to remember that double and triple bonds count as 1 bond group. And that's it for molecular geometry to get you started.